The following content has been provided by RWTH Aachen University.
I was promising you that we are going to find the lower bar of how fast you could possibly get with this interface. And for that, we need to understand a concept called interface efficiency. We know that we can quantify information as sort of the amount of data conveyed by a communication. That's information theory. You've all heard about Shannon's law and stuff like this. So in this case, we are modeling basically the information flow from the UI to the user as the information content of an interface. So when you look at this dialog here, I'm not talking about how many bits do I need to render this dialog and to make this wonderful, pretty word logo there, or the blue glowing OK button. I'm talking about how much information is this conveying to me. And you may also remember from information theory, I measure this in deciding how many options do I have to do one or the other. Like what are the different variants that can get to me? For example, this dialog here only lets me click the OK button. There's nothing I can do. It doesn't offer me any decision or something I could do differently. I just need to click OK. So measuring this interface efficiency will let us get a lower bound on the amount of information that is required for a task, which is independent of the interface design. For example, if I need to tell a system to do one thing or the other, a choice between two things, then essentially I need to provide it with one bit of information. However I do that, right? That's why we define the information theoretic efficiency as the minimal information that the task requires divided by the information that the user needs to supply. Right? If all I need to do is give the system a point like delete this file, yes or no, then I'm just providing one bit of information. That's the minimal information that the task requires. And then I can measure how much information I'm actually giving the system, like how many things I need to do in order to make that decision. This efficiency is between 0 and 1. If it's 0, it means I'm providing unnecessary information, right? There's basically no information for the task required. And that would be an example of this thing here, because when Word popped up this dialog, I don't have any choices, so I can't actually provide information to the system other than clicking away that button, right? But there's nothing I can do differently. I can only click away the button. So the system isn't getting any decision from me. It's just, now he removed the dialog by clicking the button. So the efficiency of this interface will always be 0 because it doesn't give me a choice of providing any information. If we get a little more technical, we can talk about character efficiency. So we can say, what is the minimum number of characters required for the task? Think about the temperature converter. What is the minimum number of characters we need? And what is the number of characters we actually need to enter in the UI in terms of taps? That's where it gets much easier to compute now, because now we're talking about very concrete measurements. This is, by the way, taken from Jeff Raskin's book, The Humane Interface, which appeared in 2000. He was one of the original designers of the Apple Macintosh, and he developed other systems that were really, really good at minimizing this unnecessary typing and clicking and stuff like this. Take a look at his book. His Canon Cat was a fascinating early design of a system that was very smart in terms of not requiring any unnecessary work by the user. And he goes through this example here in more detail. So read up in Raskin's book if you'd like to find out more, or if this is not clear. When we quantify information, we measure it in bits. 1 bit, obviously, we've talked about this before, right, in the UI content, information content. 1 bit represents the choice between two alternatives. If we have n equally likely alternatives, we know that the total information amount of that message is basically, if you have n equal like alternatives, the information that I'm providing is measured in log 2 of n. That's the measurement in bits. So the information per alternative is log 2 of n divided by n. And if the various alternatives are not equally likely, so not equally distributed, then each of them has a probability p of I, and then the information per alternative is P of I times log 2 of 1 divided by P of I. If you sum that up, again, you get the total amount of information as the sum over all alternatives. Notice that we need to consider this situation as a whole. So we need to determine what is the probability of different messages, of different choices of the user that is going to happen. And also, we're not talking about meaning here, but we're simply talking about measuring the freedom of choice that I have to pick different alternatives. That is the information I'm providing. You may remember old Shannon theorem. If one person sends a message through a wire and the other person knows exactly what the message is going to be before it's even being sent, we're not transmitting any information because the receiver is not learning anything new. Whereas if the message that the receiver gets could be anything out of 15 different or 16 different choices, then he's getting 4 bits of information because it's one of those 16 different choices, if they're all equally likely. If they're not equally likely, the information content actually goes down because he can guess that it's probably going to be answer so-and-so, and only sometimes he will be wrong. OK, so let's go back to the temperature converter. We've already made the assumption that we have 50% Fahrenheit, 50% Celsius conversions in terms of the direction. We're going to make a couple more assumptions here to make a good estimate of the lower bound of what is the possibly most efficient interface design. We're going to say most of the values are going to be positive, some are going to be negative. So in 25% of all cases, we get a minus sign. We still make the assumption that we have 4 characters of input. We assume we are leaving out the rare case where you don't have a decimal point. So there might sometimes be the case that you need to convert 15 or 17, but in a lab setting, it's probably going to have a decimal point. You could say in like 90% of the cases or something. So we're going to just say there's always going to be a decimal number. Again, just to simplify the computation. We assume that all the digits are equally likely and that the character input is, as we said, limited to 4 characters. So what does that leave us with? So the first obvious model we could look at is this one. This is a variant of the interface that is taking basically and making you enter a C or an F to decide what the conversion should be. So you see, if you place the mouse selection with a keyboard input, then you enter the value, and then you hit enter for the conversion. So at this point now, we're down to 1 M, the 4 Ks, another M, and another K, 3.9 seconds. The character efficiency of this one is around 67%. So we're getting pretty close to the optimum efficiency we could reach, because we know that if all we had to do was enter 4 characters, those are the only 4 things that we want to provide, and the 1 bit for deciding where we want to go, then we would be everything would be perfect. But we can do better than that. We could say, to convert temperatures, type the numeric temperature, and then follow it by a C if it's in Celsius, or by an F if it's in Fahrenheit, and the converted temperature will be displayed. Note that what we just did, a couple of people of you might have had that idea. Why have them select a direction, enter the value, and then hit enter to determine that we're done entering the number, when we could use that C or F character as the delimiter of the number and to provide the choice that the person is making at the same time. So we're just saved this poor Bob 1 character press every time he does a conversion. So now we're down to the 4 key presses, and then the final C or F, which is telling the computer the number is complete, and we decide which way we want to convert. So that's a little faster, and we're now at 80% efficiency. Yes?
What about the text? Is there, first, like I'm using this application, I have to read the whole...
A good point. What about the text? I need to read this like complex instructions? Yes, you do, but remember, GOMS is about trained users, routine tasks. So the guy using this, after 1 day in the lab, he wouldn't read the instructions anymore. he would just use it as fast as he can, right? So we're not considering the fact that people need to learn the interface at this point. We're looking at the routine user who's used it for a week or so, and is just doing stuff as fast as they can. Yeah, it's expert person, exactly. Can we do better? We're at 80% efficiency here. Well, there is one way to make it even faster. Raskin calls it the bifurcated interface. It simply does both conversions. So what you do here is you type the number, the temperature to be converted, and the converted temperature will appear on the right as you type. So what we're saying here is you enter the number on this side. There is no more any delimiter, but anytime you enter the number here, the converted value in both directions, it's interpreting it as a Celsius value and putting a Fahrenheit here, and it's also interpreting it as a Fahrenheit value and putting the Celsius conversion up here, and you read the one that you're interested in. And also, we don't have a delimiter anymore to tell the system we're done entering our number and the conversion should start, but with each character key press, it's being converted live as we go. This does have issues, but for a single interaction, that is a 100% efficient interface. Why? Because we know we need to enter 4 characters to provide the temperature, and it's requiring nothing else from us. Yes, no, maybe later. Yeah, what are you going to say?
The question was if we have, we said Bob constantly gets these numbers and then he kind of has to re-enter stuff, so how does he do that?
How does,
for single
yes. For a single interaction, we're now at 100% efficiency, but I think somebody else was asking about this, I think you guys, what about resetting the UI for the next use? Something needs to happen there. So we're not quite there yet in making this interface really work forever, because if it actually meant that before I can enter the new number, I need to press the delete key 4 times to get rid of those characters, that would make it highly inefficient. So something would have to happen here, and we can discuss later what this could be. For now, let me show you an analysis that takes this into a little more detail. Yes, there's a question.
About the previous slide, won't you have to enter an M at the end to decide which field you actually have to read? I mean, here the guy has to decide which number to shout back.
Right. Again, so you're saying, isn't there some time that I need to spend to decide whether I now need to read the top or the lower number?
Yes.
Correct. But again, if it's an expert user, he can get used to knowing if I'm doing a conversion to Celsius, I always look at the top. If I do a conversion to Fahrenheit, I always look at the bottom. But yeah, you're going like, and yes, this is a hazy thing, right? We're not talking about machines here, it's humans. So the reality is probably somewhere in the middle. It's probably going to take a little longer, quite likely, because there's more in the UI, it's more complex. It's not as simple as just having one field to look at. So there's probably going to be a little bit of picking which one I need. But in the estimate here, not as much as entering another key. So, but that's a good point.
This content was provided by RWTH Aachen University.